And this is session 3 of some chats that we're doing here at Dynamic Devices on the internet. And the idea is that we're sort of talking about the nuts and bolts of things that we need to know to do the job that we do in the embedded space with the Internet of Things, all focused on that, rather than sort of the wider sort of academic world of maybe what you get taught in university. So there's some things I don't know, there's a lot of things, there's some things I do know, there's a lot of things I don't know, and this is more of a sort of free-form conversation. And so if you've got questions about anything as we go through, raise them. It's a chat, hopefully not just me sort of talking at you and boring you to tears. So in the previous session, session 1, we talked about some really basic stuff to do with how a network works and how packets move across a network and how that relates to MAC addresses and datagrams and these kinds of things. And then in session 2, we moved on to talking about how these networks communicate with each other to form the wider global internet that we know and love and use, and often don't think about how that works. Now, unfortunately, this recording that we did for session 2, at the end of it, it cut off before the end. So what we're doing here in session 3 is a bit of a recap on some of the stuff that we went through at the end of session 2, and we'll just see where that takes us. Now, I can't particularly remember, but luckily Shreya is here and can tell me when I'm not remembering the things I need to be remembering. But I've got a bit of a list, and there was a couple of main things that we started to talk about. We talked about UDP packets, and then we were going to start talking about TCP packets. So we'll move into looking at how TCP works, the Transport Control Protocol, because that's the basis of a lot of this stuff. We also talked about a few protocols such as NTP and DNS and other things like that. So we'll probably have a bit of a chat about that, and then there's some other bits and pieces we may come on to. I'm aiming for this to be about an hour session, do these things in about an hour. So somebody give me a shout when we get to about 45 minutes and we're closing on the hour. We'll try and see if we can wrap it up, and then we'll do another session at some point in the future. Now, one thing I did want to go over and go through, I talked a little bit previously about the OSI reference model versus the TCP model. And I was a little bit vague about that, and I just wanted to do a quick recap because it's relatively important. So in the OSI model, we talked about it being a lot of layers that sit on top of each other. We've got the application layer, the presentation layer, the session layer, the transport layer, the network layer, indeed, the data link layer, and then the physical layer. Now, I'm not going to recap all the ins and outs of what we talked about there because we've been through it, but what I did want to do was just to show that that maps across to TCP, and the application layer sort of sits here in TCP, and then you've got the transport layer in TCP/IP, and the network layer and then the data link and physical are combined into the network interface layer in TCP. And you will see if you look at code and TCP/IP implementations, you've got network interface stuff, and then you've got network and transport, and then you've got application up here. So there's fewer layers basically. And there's loads of stuff on the internet about all of this, and you can go and have a look and see what you think. But what I just wanted to do here was to talk about how the physical layer, as I said last time, this is the bits of wire we talked about, and this is the media, the signal, the ones and zeros being transmitted across the wires. We talked about that. And then you've got also within this network, what the OSI model would say was data link, which is actually, say, your actual Ethernet packets going across an Ethernet network. Say we've talked about Wi-Fi before, we'll leave that out of scope for now. Think about it as similar. Then the network layer in here, we talked about the ARP protocol, the address resolution protocol, and how that maps between IP addresses and MAC addresses on a local network, and how you go through gateways to remote networks, and that sits within this network layer. And then when we're talking about end-to-end communications and reliability, we start talking about the protocols we're going to come on to. We talk about UDP and TCP, and there are other protocols that sit in here too, like SSL and TLS, which we use for securing connections. So I just wanted to recap that a little bit to show you where the things we talk about protocol-wise sit within that TCP IP stack versus that OSI model. So that bit out of the way, I then wanted to just come and recap a little bit about UDP, which is our connectionless protocol. We won't dive into it, it's in the previous session, but you will remember that we said that with UDP, you send out a packet of data, and that data goes from you to somewhere, and it hopefully will arrive, but it may not arrive. And it may not arrive because some computer in the middle, a router, is busy, drops it. And that's part of how it's supposed to work. It doesn't retry. There's nothing inherent in the protocol that retries. You send your packet, if it gets there, great. If it doesn't get there, you know, you've lost it. That's the problem. So we said that UDP is a lightweight protocol because of that, and it's often used where you need to do things in a sort of real-time manner. So if we were doing audio-video streaming, indeed as we're sort of doing with some of the Zoom stuff here, we don't really care if we lose some of the packets. We can lose a percentage of the packets and still be able to see what's going on and have a conversation. So we don't need a lot of overhead to make sure all the packets get there. And so we might use UDP for a streaming protocol and build something on top of UDP to do that. Now, conversely, if my mum is in her house with a medical button and she's got a problem and she pushes it, I really want to know that that message gets where it needs to get. I really want to know that message is not going to get dropped for some reason. So UDP would be a really inappropriate protocol by itself to use for those kinds of purposes. So it's all about use case. It's all about what you're trying to achieve. So we've talked about UDP. We'll move on to TCP here. TCP, or the Transport Control Protocol, exists because there are a lot of use cases where we do care about the data that we're getting from A to B. And there are semantics within that TCP protocol that enable the reliable transfer of data and the reliable ordering of data. And what you would think about in terms of your programming, and again, the reason that we're doing this is that most of what I would expect you to be doing in your daily life, if you're doing programming, is you're using embedded devices, computer devices, you're moving information around, you write a piece of code that connects up somewhere and sends and receives data, and you don't particularly care about the underpinnings and what I'm about to explain to you. But it's useful to know what's really going on, because if and when things go wrong, it helps you to figure out how to approach things to try to fix them. And things do go wrong quite often, so it's quite useful to know the nuts and bolts of what's actually happening. So what you would tend to do with TCP is that you would be making a connection to a remote server, and if we think about, for example, we talked about a web server, say. So I've got a web server that's sitting on an IP address 1.2.3.4, and it's sitting on a port 80, because port 80 is the standard port address for a web server running the HTTP protocol. And typically, you know, HTTP sits on port 80, HTTPS or HTTP secure sits on 443. Other protocols have standard default ports that they sit on. But again, as I explained in previous talks, a lot of what goes on in the internet is about standards and standards compliance. You don't have to run your web server on port 80, and you will have seen sometimes web servers sitting on other ports. You can run a web server whatever port you want to run a web server on. But if you don't run it on a standard port, nobody's going to know how to connect to it and talk to it and do things with it. So that's why we generally use standards. So you'd be running an unsecured HTTP web server on this computer on this IP address, which is of course very bad practice and nobody should be doing that anymore, but we're back in the mists of time here. And what I want to do is I want on my computer in my web browser to connect up to that port on that computer, and I want to use the HTTP protocol which sits on top of the TCP protocol. So remember that stack, again, it's all about that stack that we're talking about. Protocols sit on top of each other. And it's going to make a connection to this computer, and it's going to say, hey, I would like you to give me a web page, please, or if you're using an API, give me some data, please. And then the other end will say, okay, fine, there you go, there's a response, there's what you want. And what you care about is that within the logical context of that connection, your question gets there and isn't corrupted, and your response gets back to you and isn't corrupted and isn't in the wrong order. And we've already said that any individual packet that you send on the internet can take a route from your computer to another router, to another router, to another router, to the endpoint, and it might take a completely different route back when it's responding, and you don't know, and you're not in control of that. You don't actually care, except that you have to be aware of that, because it's entirely possible that this might send 5 packets of data back to you, which is your web page, and they may all take different routes, and they may arrive at different times, out of order, and that would be a problem for you. TCP exists to handle this. So the semantics of making and breaking down a TCP connection are that your computer sends a SYN packet, S-Y-N, to the remote end, and the remote end says, aha, a computer is trying to establish a TCP socket connection with me. And it responds with a SYN ACK, if things are going well, to say, all right, that's fine, you can have a connection with me. And it's allocating resources internally to deal with that within the TCP IP stack and so on and so forth. And then you, in response to the other end, to that SYN ACK, saying that you can have a connection with it, send an ACK back, and at this point you now have established a TCP connection. And you can think of that, and I think of that, as a pipeline between these two computers. And at a programming level, as with all of this stuff, there are different ways of doing things. But the standard way, pretty much everybody, I think, does things nowadays, is to use something called a BSD sockets API, or something of a BSD sockets API form, which is basically, it's a programming API. There are a set of function calls that you make to do the things that you need to do in relation to BSD sockets. And one of them will be to do a connect, and one of them will be to do a disconnect, and one of them will be to send data, and one of them will be to receive data, and there's also an ioctl thing that we can talk about a little bit. But there's a set of commands. It's all about sending data. And you can think of this pipeline as you, after making the connection, sending the data in a stream of ones and zeros, a stream of bytes, stream of information, and inside the TCP protocol it does magic so that what you send in a best effort manner will come out of the other end in the same order. So you send a stream of data in, you get a stream of data out. Inside, numbers of things can go wrong, and TCP takes care of that. One of the things we talked about that can go wrong is that I might send my stream of data, and that's blocked up into a number of packets. Those packets get sent, and they may take different routes through the internet, and so my packet 1, 2, 3 might arrive as packet 2, 1, 3. And if it came out in that order, obviously all hell would break loose. That would be a bad thing. So inside TCP, it does packet management and rearrangement, so that packet 2 won't come out of that pipe until packet 1 has come out of that pipe. And only packet 2 will come out after packet 1, not packet 3. Now, in the worst case, if there are problems, your TCP connection will block, because it will not drop packets and lose packets, and you will not see things coming out of order. That could happen with UDP. TCP eliminates that. And that's also something that can happen that we can come on to. One of these packets, I might send the packet, and as with UDP, it might go through the internet and it might get lost, it might get dropped. Now then what happens is that I'm trying to send packet 2, and then maybe I send packet 3, and the other end knows that it hasn't had packet 2 yet. And so there is a retry mechanism so that we resend within the TCP protocol, so that if a packet gets lost, it knows the packets get lost and it will resend the packet. And we have a range of different timers within TCP. There is a connection timeout timer to do with these SYNs and SYNACs and ACKs. And there is a data timer to do with whether packets are being received or whether they're being lost. And timers expire and retries happen. There are default numbers for these things, which I can't remember, and those default numbers can be changed by the use of IO controls or ioctls. And there's lots of different kinds of ioctls that you can use with TCP and TCP sockets, and indeed other bits of the TCP IP stack, to change these numbers and change these parameters and change the way things work. One sort of somewhat interesting thing is if we look at another protocol called Telnet. Can't remember which port that's on, it might be sort of 2021, somewhere around there maybe. Telnet's a real old legacy standard for having a text terminal to connect into a computer and talk to it. It's what would be, in a secure way today, you'd use SSH, you'd use Telnet in the past, and Telnet's simpler. With Telnet, you can imagine I'm on my computer, I'm talking to another computer, and I'm typing a key at a particular speed, typing my commands. Now, what might happen is every time I press my key, if it sends my packet of data over that TCP socket connection to the other end, you can imagine, we talked about in previous sessions, my payload for my packet has headers in front of it, and those headers build up through the TCP IP stack. So there's relatively quite a lot of overhead. So my single byte of key press could result in a packet with quite a lot of bytes. And if we sent a packet every time I press a key, that's quite a lot, that's a multiplier effect. And if everybody was doing that, then there's a lot of overhead across the internet. Now, the internet you know and love today, we got lots of bandwidth, we got lots of computers, we're sending videos, so you may think, well, who cares about sending a lot of packets for a lot of keys, that's nothing. But remember, this is coming from a time where there was a lot less bandwidth and a lot less computers, and we cared a lot more about this stuff. Also, it's bad practice to waste resources that you don't need to be wasting, because this stuff scales up. So there's something called, I think, the nagle algorithm, and what it does is it sort of buffers up over a period of time the things that you're doing in expectation of it being a sort of time-limited set of key presses, say, and then after a bit of time, it'll send a packet. So instead of sending one packet every time, it'll go, well, I'll wait a bit and I'll send some stuff. And you may not want it to do that, because you may not be sending key presses. You may have some other reason that you want to send a little bit of data immediately. And you can use something like an ioctl call to disable that. So you can turn things on and off, and you can find a big long list of all of the socket options that you can use and you can change. And it's worth going through those, it's quite informative. And it's all to do with timers and turning on and off facilities of what they want to do. We have a junior engineer with us today who clearly, it's okay, clearly doesn't like the nagle algorithm. None of us do. The nagle algorithm is a problem, the nagle algorithm. So he's going to take a little break. So that's how it works, basically. Now, a lot of what can happen as well is stuff goes wrong. And this is what I'm coming back to. When everything works, you don't really care. You're getting on with what you're doing, but things go wrong. And then you need to care about why things are going wrong. And you need to be able to take an approach, a logical approach, as an engineer, to drill into that, to try to fix it in an efficient kind of way. So you may be sending a SYN packet through to the other end, and there may not be any service running on that port on the other end, because there's no web server there. And in that case, if you're able to talk to the computer, to the TCP IP stack in the computer, that will respond to your SYN request with, I think it's an RST response, saying, can't do anything here, we haven't got a service that you can talk to. And that also can tell you some stuff, and there's a kind of crossover between the nuts and bolts of the internet and us as engineers trying to make things work, and hackers and hacking and what they do to try to break into systems. And they use a lot of knowledge about the underlying mechanisms of how things work to find weaknesses and to break into things and be places that they shouldn't be. Now, an an example of this is that if I want to know if a computer exists, we talked about his ICMP ping in previous sessions, I can use that. It's good practice to respond to a ping. Sometimes, and people think for security reasons, they won't respond to a ping, so you can ping a computer, get no response. So you think it's not there, but it is there. And so what you might do as a hacker, if you're trying to work out if a computer is running a service on a port, you might send a load of SYNs to computers on different port numbers to work out what ports are open, what's listening on what port. And then where you get responses, firstly, if you get a response, you know there's a computer there, which you didn't know before. And also, if you get a SYNAC or an RST, you know which ports open and have something listening on, which then tells you you can go off and do other things to try to work out what might be listening on those ports, and you know, perhaps do naughty things to try to break into a computer. And again, as I say, no service has to listen on any particular port, so you might run through all the ports. And I mentioned last time, TCP, the port number, is codified in a 16-bit value, which means you have around about 65,000 different possible numbers of ports. And there are various attacks that you can use on computers in these ways if you're a hacker, and one of them is a SYN flood, which is where you send lots and lots and lots and lots of SYNs to a computer to try to overload it and take it down. And this is one of many different styles of attack that you know you can use when you understand the nuts and bolts of how the internet actually works. Similarly, and something that we care about quite a lot with the kinds of IoT devices that we put together, you might have a computer A which is going through, say, a cellular network to computer B, and a cellular network particularly can be unreliable. You know yourself, you get in reception, out of reception, and you know you can run into problems. So what might happen is your device establishes this TCP/IP socket connection, and then your cellular coverage goes, and so you're no longer in coverage, no longer able to talk, but the other end won't know. As far as it knows, you're there. You know, how does it know? It doesn't magically know that you're not there. So if you knew you were going to be disconnected, then you could send a disconnection packet through to the endpoint of the TCP socket, and then it would be a RST, and you would get an ACK for that, and the connection's closed down. That's great. And you would do that as a good actor in closing down a TCP connection, say after you've retrieved your web page, because you don't want to waste resources at the other end. But if your connection goes down, you haven't done that, so you don't know. And the only way that you can know this stuff is if you have some kind of timeout. And after that timeout expires, it can then be assumed that the connection is no longer alive, no longer viable. And so you have something within TCP called the TCP KeepAlive. And what will happen is that you're using your TCP socket connection for transferring data, and after some time of inactivity, if you haven't transferred any data to do whatever it is you're trying to do, maybe because you haven't got any data to send, it's just sitting there, then internally within the TCP/IP stack, the TCP socket, it will send an empty packet, a KeepAlive packet, just to tell the other end, I'm still here, it's all okay, things are going on. And that's how you keep the TCP socket alive, and that's all transparent to you, that just happens. Again, you can change the rate at which these KeepAlives happen with ioctls over the socket connection. As I've said before, this is all somewhat abstruse and academic, and the real way to get into this and understand this clearly is to run something like WireShark, to run a packet sniffer on your networks, and you can see all of this stuff happening. It's not secret, it's there for you. The only reason you don't see it on a day-to-day basis is you don't need to. It's complicated, but you can run WireShark or an equivalent packet sniffer. WireShark's open source and free and fantastic. And WireShark will sit on your interface, say a wired Ethernet interface, showing you all the packets going through the interface, and it will break them down and disassemble them and show you what every bit of every packet means, what the protocols are, the ARPs, the DHCPs, the TCP connection and disconnection, the data packets, the retries, and you can see exactly what's happening. Now, a couple of things to mention here. With our computer running in a usual way, we generally only care about information that is for our computer coming into it, or the information we're trying to send out of our computer. There are some other kinds of packets we talked about called broadcast packets and also multicast packets, which have specific purposes, which we always see. Broadcast kind of means that. But in general, we really only care about packets for us, for our IP address. Now, if you're listening on your adapter with your TCP IP stack and it's all set up so that at a higher level you only see packets that are for your IP address, all the other stuff you won't see. And that's not tremendously helpful if you're trying to get a view of wider network activity. So what WireShark will do, and there is something called promiscuous mode. Promiscuous mode is a particular mode you put your adapter, your physical connection to that bit of wire or indeed Wi-Fi into, and it will then propagate all the packets that it sees up the stack so you can see them all. So you get a lot more information when you're seeing everything, even the stuff that's not for you, but you want to see that when you're trying to establish where things are going wrong and what's happening with network activity. Typically, you'd have WireShark running on your computer on the network, and you'd be looking at the packets going between a device that you have under test and another device running a server that you have under test, and you'd be seeing what happens and trying to work out why things aren't working correctly. So you want promiscuous mode to be able to see that. A brief, seeing as we're going through all of this to cover it properly, nowadays when you connect up your RJ45 connections on Ethernet into your computer, they go to something called a switch or a hub. In the old days, it used to be a ring. We had token ring, and everything was connected in a big circle. And then you had a really big problem, because if something got broken partway along, things wouldn't work anymore, and you'd have network admins crawling all over the building trying to figure out where it was broken. That's gone away now. Nowadays, you see anywhere we have these switches, and they sort of aggregate connections. You have switch panels, you have RJ45 connections. And the problem you can run into is that in the old days, these were very dumb. And what would happen is you'd have all these computers, and you could put your WireShark device onto this, and you would put them into promiscuous mode, and you would see everything. But nowadays, they're quite clever. And what they will tend to do is not propagate all the packets from every port to every other port, because that's a lot of information and a lot of information being propagated. And so you can run into a problem where even though your WireShark is in promiscuous mode, you're not seeing stuff from other computers. And when that happens to you, you need to start looking at the switch box or the router you're going through, because it might be smart and it might be protecting you from all this data. And you need to, it's often quite useful to have an old dumb switch box around and about when you need to do testing. So that's that stuff, and that's WireShark. We'll mention Wi-Fi. Wi-Fi is similar. Wi-Fi is a broadcast medium, so inherently, because we don't have bits of wire, you can pick up everything that's going on everywhere on a particular bit of radio spectrum that you're listening to. You have promiscuous mode for WireShark adapters 2. You can run promiscuous mode for network adapters 2. You can run WireShark on those. You can look at Wi-Fi packets. It very much depends on the chipset that you're using for Wi-Fi and the drivers that you have for Wi-Fi, whether it will correctly allow you to enter promiscuous mode. And one of the problems you often run into is, even having a little bit like this, even having set everything up correctly, you're still, there's something missing, and you're only seeing packets that are for your computer. You're not seeing everything that's going across the entire Wi-Fi network. That's a problem, and really you need to look at the chipset that you're using there and the drivers that you're using, and possibly use a different computer if that's a problem for you. Similarly and briefly, I'm getting slightly off the topic because I wanted to finish up on TCP, but with Wi-Fi, there are two different sort of levels that you can look at this stuff. You can look at TCP IP packets on your Wi-Fi network. So that's your SSID that you're connected to on the frequency within the Wi-Fi radio spectrum that that network is on. And there are other Wi-Fi tools where you can look at all the data that's going on all the different Wi-Fi networks across lots of different channels. And those would typically be things called Wi-Fi scanners. And again, those kinds of things are quite attractive to hacker people who want to go into a space and take a view on all the activity in that space. And there's a few different things. You can go and Google for the pineapple, which is one of these things, and then there's a zero something or other, zero flicker or something. It's not quite right, but that's something people use to access and indeed break Wi-Fi networks. But I won't go further into Wi-Fi at the minute. So I think that's what I wanted to talk about really, that we, in a lot of use cases, we care about getting that data from A to B and doing it with retries and in a reliable way. And there needs to be a way of doing that, so that's TCP. For us as application level engineers, mostly we don't care about that, we just rely on that to work. That's how it works. Big problems for embedded systems can be when your cellular networks are flaky or other Wi-Fi networks are flaky, particularly with newer LP1 networks like NB-IoT, Sigfox, LoRaWAN. This is all relevant to packets and packet loss and packets going missing and packet retry and reliability of data. And I think that's what I wanted to talk about with TCP. Now, I think last time, and tell me if I remember correctly, Shreya, but we then talked a little bit about the fact that when you're using your web browser, you can, but most people tend not to, enter IP addresses. Yeah. We know that it would be somewhat pointless to be trying to enter MAC addresses because they're only for your local network. But there isn't any reason you can't enter an IP address into your browser. If you've ever tried that, you certainly can. And that would be of the form, IP address, port number. And with a browser, with the protocol actually, if you drop off that colon, then it will use the default port number, which would be 80 for an HTTP connection. Now, for HTTP, again, it's a protocol and it specifies how you construct the connection that you're going to use to a remote computer. HTTP sits on top of TCP. And in the simplest of cases, HTTP goes through that TCP connection process, and then it sends a text line saying get something or other, and I forget the exact semantics, but it sends a get, and then the thing it wants to get, and then the version of HTTP you're using. And a web server at the other end interprets that and responds with the response to your get request. Now nowadays there's a lot more that goes on actually. Within this request you can also have headers which tell the other end things, and you can have a data payload as well, sometimes in some cases, which sends data to the other end. And then there is a response format. And the way to look at this, you can go to WireShark and you can look at the packets and it will deconstruct those packets and show you those packets. An easier way nowadays is if you go within your browser, I look at Chrome mostly, but there's generally a sort of a developer mode, or developer options. And if you bring that up, if you open that up, you'll have all sorts of things that you can see, and it will show you the network traffic that's going in and out of the browser, and you'll see all of these get requests and responses. That's kind of an easy way of doing things. If you care about this level of protocol, application level of the TCP/IP stack, easier to go into the browser instead of setting up WireShark all over the place. And this, sometimes you need to get into, because again, you're trying to do things, and we've done this with some of the work we've done with Belina. We've been running servers, we've not been getting responses, the web pages haven't been displaying properly, we don't know why. It's because there's some JavaScript running inside those web pages, it's failing, but we're not seeing why it's failing. And you can go into this developer mode and you can see those individual connections failing for some reason, try and work out what's going on. You can also do that with WireShark, as I say. But what I was going to say was, so we're putting this HTTP connection together. As normal people, we're probably not going to go to IP addresses because we can't remember them, and computers do change IP addresses periodically. So what we tend to do is enter some kind of URL for a domain or a subdomain. And we know about domains, you know, domain for dynamic devices is dynamicdevices.co.uk. And what happens is that when you go to your browser and you type in www. I'll use something shorter, google.co.uk, the browser talks to the TCP IP stack, and you're trying to make a TCP socket connection through to this place. But the computer, your computer, computer A, trying to talk to the server computer, computer B, it doesn't know where that is. And it can't just talk to that, it doesn't know about that, it talks to IP addresses. So you need to be able to map between the domain and the IP address. And that's where this thing that we know about called domain, DNS, domain name system, comes in. And what happens is that your computer knows, because it's configured, about the domain name server, and there are lots of different ones. And when it needs to convert a domain into an IP address, it sends a request using the DNS protocol to the domain name server for the information it needs to get that IP address. So that will happen before it can establish a connection, and having got that IP address, it can then go through those semantics of establishing a TCP connection, and on we go, and on we go. Now, domain name servers are, is that still recording over here? Very good. And what time are we on?
38 minutes.
Very good. So domain name servers are thought of, as I understand it, as basically a distributed database of information. And you set the information and configuration for your domain, and it goes into your local domain name server, and then that's propagated across the internet. So it may be that if you set up sort of domain name server 1 over here, and somebody else is using domain name server 10 over here, they may still be getting old information until it's propagated across the internet. So that can also be a problem. And sometimes you want to check, and what I would be doing is saying, if I'm pinging a domain, and if that's my domain and I'm changing the details of the domain, you would then go and you would do your own domain name requests to make sure that what is being returned is what you changed, because there is a latency between updates happening. And it can be that you've changed your information on the local server and you're using that and it's fine, but the person you're working with on the other side of the world is using different servers which haven't yet been updated, and it will be different for them. And unless you know that this is how it works, you can be wondering why on earth it's different for them, but it's only because it hasn't propagated through. There's a tool that you can go and investigate called Dig on Linux. I don't know if it's on Windows, and that's a kind of Swiss Army knife of enabling you to do different kinds of requests to different kind of domain name servers for different kinds of information, and it gives you a lot of information back that you can analyze and deconstruct and figure out what's going on. And what I should say also is that, you know, if you register a domain with the likes of GoDaddy or whoever it might be, and you're in control, I mean, you know, it will by default try and manage all this stuff for you, because most people don't care, they're just trying to run a website. But if you do care about this and you go into the DNS record management system, then you'll end up with a load of rows that you can put entries into. And one of the types of mapping that you can make is to map between a domain name and an IP address. But within DNS, there are other kinds of mapping that you can make as well. And you can also have entries in there which aren't mappings, they're just informative. And examples of this would be, you've got a CNAME, you've got an anchor, you've got an MX record, and you've got a TXT record, which are the ones I tend to deal with mostly. Now an anchor, if I remember this rightly, that's the one that maps a domain to an IP address. And particularly, what I could do is if I've got Google, and I'm mapping that through to IP address A, I may have a subdomain, I don't know, apps.google.co.uk, and then there might be a record in there which maps it to a different IP address. So subdomains of domains don't have to be the same computers. We kind of know that with knowing how things work, but it's just important to bring that out. And you can have lots of subdomains and sub-subdomains, I think all over the place. You can set all that stuff up. So you can have, we could have a production server, which is one computer, a development server, which is another computer. We could put them on different domains and there would be different things. And of course, it's easier for people to remember. Now, this doesn't know about or care about ports. Ports is to do with the TCP IP stack and TCP and UDP protocols. So it's not ports. This is about mapping domains to IP addresses. MX records are for email. When you send an email, I won't go through the email protocol, but when an email gets sent to a particular domain, it needs to know how to go to talk to the email server. And it doesn't know unless you tell it. So what will happen is it will do an MX lookup on the domain server to ask it what the IP address of the right, or what the domain of the IP address is of the right email server. And actually you can have multiple MX records of different priority. So try that one, then try that one, then try that one, then try that one for reliability. And then lastly, a text message is sort of what it said on the tin. It's just a bit of text. And that can be used for different purposes. Typically, if you're trying to set up some services in the cloud, you might be asked to prove ownership of your domain. Because if I didn't have to prove ownership of, say, Google, and was able to do things to set up around Google, that would be, in capital letters, a bad thing. So when you're trying to set up cloud services around domains, it will say, okay, well, I need you to prove ownership. And there are different ways. But one of them is it will give you a long string of sort of like passphrase like random data, and it will say create a text record within your DNS server for your domain, which you only have access to because you own that domain. And then it will go and check for that text record and say, aha, yeah, you've put in, you have to wait for it to propagate, but it will go and check for that and say, right, well, you've entered what I asked you to enter, so I know you own that domain, so now you can proceed, you can do stuff with that. That's how that works. Another mechanism that's more recent that people use is, I don't really understand, to be honest, but there's a lot going on spam and the annoyance of people sending all these like spam emails and dodgy emails to try to scam you. And so there's an effort to use crypto in text messages to prove that where your emails are going from and coming to is authentic. And nowadays, and I get this sometimes, you go through Google and your emails get dropped because it will say, we can't authenticate that this is coming from a true place because you haven't got all that stuff set up, and so you have to go through these processes. And this is now sort of moving more into network admin, I would say, which is not what we're concentrated on here. We're just concentrated on the IoT side of things. So DNS servers, the kinds of records you get in DNS servers, and then the mappings that you get between these different entries here. And that sort of, well, probably we need to talk about URLs now. So the URL, again, is just a standard format for how you put data together and is used predominantly, we know about web servers, but you can use it in other ways. But if we look at an HTTP URL, and you will get the protocol prefix, which in web server parlance would be your HTTP bit. And then you would get the server, which may be an IP address, or it may be a domain. And if it was a domain, all of this comes into play internally to do the mapping. And then optionally, you'd have the port number, 80, but it could be anything. And then after that, I mean, it may just be that, but after that, you may have a path to a particular resource. Originally, that would have just been sort of a static page of data, mostly an HTML page. But we know, particularly with microservices and APIs now, that might actually be pointing to some kind of dynamic service, which is going to return some dynamic data to us. A lot of how things work nowadays. Then after the path, you end that with a question mark, and you can start providing data as a set of get parameters to the server. And they go in key value pairs. So, you know, key 1 equals val1, ampersand, key 2 equals val2, and on it goes. And you know that because if you look at the top of your browser, there's weird stuff going on when you're doing your eBay or whatever it might be. And there's a load of that stuff, and that's generally to do with providing parameters and state information. It's probably not a recommended way for a lot of purposes nowadays. It's still used for lots of things. It's sensible for lots of things. It's not always sensible. And you know, you can imagine maybe you've done a search for some data on a list, and it's returned the kind of data in the list that you've searched for, and then it pushes a button to get the next page or something. Well, the way that that might be handled is that within these parameters that are sent when you push that button, it tells the bit of code that's running on the server where you were. You know, so I'm looking at the first 25 and I've pressed next, so it knows to give you the next 25. That's the kind of way that that stuff would work. One of the problems with that, well, and I should say, because of the construction here, some characters are not allowed in the data that you're sending. You've got the name of the key and some value data. Now, ampersand is used to separate these keys and values, and question mark is used to indicate that, you know, this part of the URL, and we've got slashes as well. So some stuff is not allowed within your key naming and data naming, and that's why we do something called escaping or URL escaping. And essentially what that does is any character can be replaced with a %, and 2 digits, which are the ASCII value of the character. And similarly, I think, you know, percent is for a %, and things like that. You could look it up, but that's why you will sometimes see that these odd % characters are in your URL line when you didn't type them, and it's because for it to be a valid URL, the URL has to be escaped for transmission, and the browser will automatically do that for you. And if you're trying to do things with URLs and you don't escape them, then you can run into a lot of trouble because it won't know how to interpret the URL properly. And that is sending parameters on a get URL. And again, we talked last time about there being actually a number of different methods to do with HTTP. There's get, there's post, what did we say? Delete, put, and can't really reach down there, delete. And the two that are generally used are get and post. When you type something on your browser line, it'll do a get. Now, I told you there are other ways of doing things other than sending parameters on a get line. And the other way of doing things is to use a post. And what the post does, and I'm running a little bit out of space, but I said when you do a get, you've got the get, and then you send a bunch of headers, and you've got your line here for what you're trying to retrieve, and your URL with some data on it. But if that was a post, instead, you would be posting to your URL and you'd have some headers. But because it's a post, the web server would know that after those headers, you now have a data payload. And so the data that you can send on the get line, which you can see in the browser, another way of doing this is to format up some kind of data in the payload, and then the web server can pick that up. It knows it's a post, it knows there's some data, and then you have to work out within the web server how to interpret that data, because you can use any format that you want. Generally, that data, I think, would be MIME encoded, which is encoding non-representable data values, like a 255 isn't representable as a character, and it changes this binary data into 7-bit data, which is representable as characters. I won't deep dive into that. Just be aware that there are different ways of encoding your data when you send it, and particularly within posts. Then there's another couple of ones which I can't really remember. I think put was more to do with automated systems, because all of this stuff was designed, and we go back to Tim Berners-Lee, and it was much more than just, you know, browsing for whatever's on the newspaper website today. Put is, I think, enables you to send data objects to places, and delete, I think, enables you to delete those data objects. Now, typically, the way most of us use the internet today with web browsers and things, that's not relevant. There's something else called WebDAV, which is yet another protocol, which I think leverages HTTP to allow you to move files around between remote computers and your computer, and that would probably be much more interested in using puts and deletes and those kinds of things. So that, I think, is what I wanted to talk about in terms of DNS.
Yeah, I have a question.
Fire away.
For URLs,
Yep.
Is there any structural difference between private URL and public URL?
Right. Right, interesting. So I don't understand that question. What is a private URL versus a public URL?
So it's like a local URL and public URL. So one is you can only access within the...
Right. So the answer is no.
Okay.
The URL is a standard. There are protocols within TCP IP, like HTTP and so forth, and FTP, and other protocols. They require your URL to be correctly formed.
Okay.
And if your URL is not correctly formed, it is not right, and it is broken, and things will break or behave in unexpected ways. So standards compliance. It's worth saying that the way the internet is constructed, and we talked a bit about RFCs, the best practice is when you're doing something, you should be as tightly constrained and correct as possible. When you're putting data out there, say. When you're putting an implementation together, you should be as accepting of slightly different cases as possible, so you're not fragile, you're not breaking all over the place. And so you try to be as exacting as possible in what you're creating to the specification, but if you're handling stuff other people have done, you try to be, within correctness, you've got to be correct, but you try to be as accepting of things as possible. It's sort of a best practice idea there. To try to maybe explain that a little bit better, you know, we are in control here. We can do whatever we want with these TCP/IP standards. If we're talking to the rest of the world, then we have to obey the standards because they won't understand us if we don't. But we can run our own DNS server in this building. People do. Companies run their own DNS servers. And so we could set up, you know, dynamic devices.cc. .cc is, I was going to talk about TLDs, so I'm going to talk about TLDs in a second. .cc people will often use to indicate something which is local. It's not publicly available on the internet. And we might set up dd.cc, which has records in our local DNS server, and our computers on our network know about our local DNS server, maybe as well as public DNS servers. And so when I go and I use on my browser dd.cc within my URL, it goes off to our server and it maps that to a local internal IP address that other people can't see, and we can get onto that and we can use that for maybe jobs that we're doing. We might have our own Git repository locally or our own wiki repository. Nobody else can see that on the rest of the internet. And nobody else can map from that domain to that internal, so maybe like 192.168 type of computer, because that's only local to us, but nevertheless we still have to use the right URL formulation. A slightly different thing that might bring it out and that you can do is that if you type a different kind of URL protocol into your browser, if you type ftp : / and an IP address, and again I can't remember what an FTP server sits on, that might be port 21, I might be wrong, but there is a standard port for FTP, and if you don't add a port after the colon to tell it, it will use that standard port. And your browser, because your browser supports FTP as well as HTTP in almost all cases, what it will do is it will try to connect using a different protocol, not HTTP, using the FTP protocol, which sits on top of TCP as well, because we need our data to be reliable and accurate in the right order and all the rest of it. And that goes and that connects to a server, and an FTP server is a file transfer protocol server for transferring files. As it's, again, I've said this before, but you know, we're pretty much, you know, what it says on the tin with these names. And FTP, the FTP protocol lets you get a list of what the files are and authenticate in and send files and receive files. We get the point. You can look at the semantics of how FTP works, and what you will do is you'll get a basic file layout in your web browser. And that's not an HTML page. Well, it kind of is, but that's not part of the HTML protocol. That's being built up by the browser from the FTP protocol. And there are other protocols that you could use instead. I can't think of any offhand, but this is somewhat of a different usage. But if you want to change settings in browsers nowadays, there's generally a settings protocol prefix which tells the browser this isn't an internet-y talking to other computers thing, this is an internal reconfiguring the browser kind of thing. And so that settings protocol is linked to an internal configuration option set of pages that it generates inside the browser, so that you can change all sorts of magic settings that you wouldn't otherwise be able to see. So you can change that protocol, and that's why it's there. And that sort of, you know, I suppose what I'm saying is that if I had, we don't really use FTP for a lot of purposes nowadays. There are other protocols people use, and often because FTP itself isn't secure. But what you might do is you might have an FTP server running on an embedded device, and you might want to copy those files off locally on your local network, and then you would type, say, on your command line, FTP, I mean, you could do this in the browser, but you could do in your command line, FTP to a local IP address, and then you could start using the FTP program to do stuff. In theory, you could just do FTP to your local domain, which goes off to your internal DNS server to point to your local computer that you can talk to on your network and nobody else can talk to. So hopefully that helps. But yes, the URL standard is the URL standard, and you have to adhere to that. Good. What's the time?
Yeah, it's almost 1.
Okay, so few finishing up bits then. Because last time we talked about TLDs, didn't we?
Yeah.
I don't think we talked about them, so we'll talk about them. TLDs, top level domains. And you know all about this. You've got .com, America, you've got .co.uk, the UK, .whatever it might be. A lot of these TLDs, and certainly initially, were country specific.
Yeah.
And there are other ones. You've got, for example, within the UK, we've got .co.uk, as I say, which is companies in the UK. We've also got .ac.uk, which is academic institutions, and that's why your university emails are as they are. You've also got .gov, gov.uk. What you tend to find with America is you might think that in America it would be sort of .gov.us or .com.us, but it's America. So they don't, if we're not telling you different, it's America. Because, we're America. So that's why that's slightly different. And you just, if you don't see the country, it's America. And all the other countries, and then more recently, there's been this explosion of other kind of non-geographical TLDs. There's millions, aren't there? We've got .io, .me, .app, you name it. Now, there is a root server for every top-level domain, which controls that root domain. And there is, I think this is right in saying, the actual legal structure differs a little bit, but essentially you've got a company, some form of corporate structure, which is in control of a particular TLD. And so, for example, in the UK, it's, who did I say it was? Nextel. Ooh, I should know that. Can't remember. It'll come back to me. And something or other. And if you want to register a domain against that TLD, you go to them to do it, and you pay them money to do it, and they keep the note that you own that domain, and you can use that domain, and you renew with them, and blah blah blah. And they generally don't Nominet. So I was thinking Nominet, and there's different ones in different countries. And generally, for any given country, they would want that corporate structure or legal structure within the country, so they run their own. Different countries run their own stuff, and they generally don't want millions of people talking to them all the time about this stuff. So if you tried to talk to them and register with them yourself, it would be quite expensive. So instead, you go through an intermediary, and that's where your GoDaddies and all the rest of it make their money. And they have block deals to do block registrations of things. So you go through your intermediary, pay them some money, but they're not in charge of this. They're an intermediary, and depending on, you do a search for .io, and they will propagate your registration to the appropriate management entity of that TLD. And that's how that stuff happens. And it all appears to be very automated nowadays, but it just sort of goes on behind the scenes. So that's TLDs and how TLDs work, and there are different pricing structures for all these different things, and you see that, you searches, some domains are costed in different ways. So that's TLDs I wanted to talk about, and then I suppose a little bit that I just wanted to finish up on, sort of more random stuff, is things like maybe a couple of other protocols that are supported that we use within the TCP IP stack. Sorry?
MQTT?
Yeah, we will talk about MQTT, but I think we'll do that another time.
Okay.
Because MQTT, we can spend session on by itself, I think. There's quite a lot going on in there. But basically, I'll briefly say that MQTT sits on top of TCP and the TCP IP stack. And the idea is that TCP, I've explained, gives you this best effort, reliable way of moving data around. But also that TCP you think of as a stream. And I should have said as well, I meant to say, it's obvious, but I meant to pull it out, that it's bidirectional.
Oh, okay.
You can be sending data in both ways. And we need to talk about that at another time. Remind me to talk to you about client server. Because people get very, very confused about client server, because there's a bit more to it than people think. But basically, TCP, I think of it as a pipe, and information flows through both ways in that pipe at the same time. And MQTT changes that a bit, because in our world, we need to be able to move this data around reliably, but we also need to know what the data is. And if you've got a stream of data, it can sometimes be hard to work out which bit of data is which and what's going on. And what MQTT does is the API, or the way that you interact with this protocol, is you send message objects. So I can send my message object, which goes through that TCP pipe, but MQTT handles turning that stream of data into these individual messages, which are much, much easier for me to deal with as a programmer. There's more to it than that, but we'll go into that next time. I will say also that there's a newer protocol called MQTT-SN, which is MQTT for sensor networks, which is under development now, and that uses UDP. Because a lot of some of the stuff that MQTT does sort of replicates what TCP does to reliably transmit information. And some devices and some radio communication systems, and NB-IoT is one of these examples, they don't really leverage TCP well. There's overhead involved in TCP. You know, we were talking about, you've got packets that are retrying things backwards and forwards and all the rest of it. What MQTT-SN does is to do the bits of the TCP retrying to make sure that an object gets from A to B, but it uses UDP, so it can be implemented on a more basic kind of platform, like a microcontroller that maybe doesn't have a TCP IP stack. So we will come on to MQTT. We will talk a bit more about client server because that's quite important. And I just wanted to finish up and talk about other random protocols because there's all sorts of stuff, and one of them that we care about a lot is NTP. That's the network time protocol. And similarly, what happens is you've got a network time protocol client on one computer, and it knows about some servers running on IP addresses on other computers, and often you've got an embedded device which doesn't have a battery, so it doesn't know time. If it goes off, it can't do time. And also, even embedded devices that, when they're on, they can count, but depending on some of the modes that you put them in, sometimes they lose accuracy over time. In particular, a standard RTC clock in a computer is specified to lose about a minute a month. That's a problem if you need accurate timekeeping over years. And one of the things you need accurate timekeeping for is crypto, which we'll talk about again another time. But when you're securing devices and you're using public key cryptography, you're using certificates, and without going into the nuts and bolts of that, these certificates are dated and have expiry times. And what that means is that if you're trying to do secured comms from your embedded device, and your embedded device has the wrong time, the certificate will be invalid. And in the worst of cases, and this has happened, embedded devices that have the wrong time, or if a certificate expires upstream, you can no longer talk to them. Now you can imagine what a big problem that could be if that caught you unawares with your 100,000 devices that you've deployed all around the world that you can no longer communicate with. That's a big problem. So you need to be able to get the time. The protocol that you use is SNTP, Network Time Protocol, or I think what we actually use is SNTP, which is the simple Network Time Protocol. It may seem easy to get time. Time, oddly, can be a really complicated and hard thing to deal with in computers, strangely enough. And in particular, for example, if you say, okay, I'm sending an NTP message now, I want you to tell me what the time is, and it goes to this computer, and the computer says, okay, here's what the time is, and it sends the time. But it's taken some time to do that. And there's some jitter and some latency in these packets moving around the internet. And there's some jitter and some latency in these packets moving around inside your computer. So how accurate do you need to be, and how do you manage that process to gain that level of accuracy? And that's what the protocol does. And the simple one, I think if I remember rightly, you don't always need super accurate time. You need time down to say the millisecond, and SNTP will give you pretty accurate time. Another example I mentioned last time of problems that you can have, which goes back to DNS. It's generally, I would say, pretty bad practice to hard code IP addresses into your embedded systems software, into your firmware, or into any application really, because that IP address may change. You may lose control of it. I mean, IPv4 we talked about, we've basically exhausted the available number of IPv4 addresses, so there's contention for these addresses, they need to be reused and recycled. So your IP address, it's possible it may change. I need to qualify that and say, if you're paying for a static IP address, unless things go very badly wrong, it's not going to randomly change. But if your contract came to an end or something, you didn't renew it, you could lose the IP address and you wouldn't be able to get it back, these types of things. Now what some people did with some embedded devices was that they needed to get time, and they hard-coded some IP addresses of network time servers on the internet, because there's lots of them, into the firmware. And sadly, they didn't consider that the company doing this work, they didn't own those network time servers. They just got some random guy's network time servers. And so he was getting all these sort of requests to his network time servers, which he wasn't bothered about. But after some period of time, he shut them down. Because he can, because he just didn't want to do it anymore. And he immediately got a lot of emails saying, oh my God, what have you done? You've shut down these servers. Well, yeah, I have, so what? I can, it's mine. And they said, well, yeah, but we've got all of these devices everywhere, and none of them work now because you've turned off your servers. Well, it's not mine, why, you shouldn't have been using my stuff. And that's another very important thing. So, what are your third-party external dependencies in your system, and what happens to break your system if the stuff that's not under your control changes, like this? Now, this guy was a nice guy, and he said, oh, I'll turn them on for you, and I'll leave them on for 6 months, and you can sort yourselves out, and then I'm going to turn them off then, So it all worked out okay. But you can imagine the position if you woke up one morning and suddenly found, your entire product line had stopped working. You have no idea why. And that's more common than you would think with embedded systems. And one of the things that's always in my mind is, what is the stuff that I don't know and don't understand and aren't thinking about that may come back to bite us in 5 years? Where are our plan Bs here for when this stuff goes wrong? So what I meant to say with that is, yes, stuff goes wrong, what are your dependencies? Also, better practice to use a domain name mapping in your code, because then your embedded device will go off to the domain name server, which is under your control. And if you need to change those mappings, IP addresses or whatever it might be, you can, because you're in charge of that stuff. But it'll take a little bit of time to propagate. Stuff is cached in devices, but in the very worst case, you could probably just turn it off and turn it on again. That's sometimes difficult, sometimes a problem, but at least it's possible, as opposed to broken. So NTP, loads of other protocols we could talk about. I think next time we'll come on to talk about client server. We'll talk about Bonjour, Zero Conf and address collision, MQTT, maybe a bit of Wi-Fi, and we'll see how that goes. So, before we wrap up, any more questions from anyone?
Okay, what I want to ask is, talking about the DNS name, since we know the DHCP actually assign the IP address, probably in an automatic way. So when you have a unique DNS name that you want to use, so how do you generate the IP address? Is it the same way as the DHCP assign it, or that's the first, your DNS name now, definitely to have an IP address. Do you generate that on your own, or is it DHCP that does that? Okay. Because what I understand is that DHCP do subsequently for some other system that want to join, which is every system that is connecting an IP address.
Right, so I'm not sure I understand. I'll try and answer that, and you tell me if I'm answering the right question. Okay. It sounds as though what you're sort of saying is there's this process to set up DNS and DNS to IP mappings, or domain to IP mappings, and we know IP addresses can change. So what's going on here? What's the process here? Okay, well, there are different processes. So if I set up my computer and I pay a network access provider, if I want to be on the internet, commercially, say, then I'm probably paying somebody for one or more static IP addresses. Now, having said that stuff will change, yeah, it does, but contractually, if I'm paying somebody for a static IP address, unless very odd things happen, like they go bust or something, that's not going to change. And so, in general, with that kind of setup, over periods of months and years, IP addresses don't change. I think we talked about, I've got an IP address I pay here for does, a public one, and that just sits there, and it will be the same until I stop paying for it. But when I stop paying for it, it'll be freed up, and somebody else might use it. And if I want another IP address, it would be very unlikely I wouldn't be able to say, I want that one back, please. It doesn't work like that. Now, internally on internal networks, we know that I'm going to a DHCP server, and that's giving me a dynamically assigned IP address. Quite often, you know, if it knows that I've got my MAC address, you know, and I've had an IP address and it's free and it's clever, it'll give that back to me. So it might not change too much. But there's no guarantee of that. And it might just give me a completely different IP address, and it might, and I have no control over that, and I have to be aware of that. Equally, if I'm on a computer, and this is particularly the residential case, if I'm using a residential communications provider like Virgin Media, somebody like that, I've got my internal computer network, and then it goes through their access point box, and internally it's handing out DHCP addresses to my local network, and externally it's got a public IP address on the internet, and that's being handed out upstream by their network, and that changes. And you will often find, if you go and look at your, you know, if you do your browser connection to the port that the web server is running on the box, and you log in and you see what's going on, you can see the public IP address, and probably, quite likely, if you power cycle the box, you'll get a different address. Because you have no arrangement for a static IP address. There are numbers of sort of tech-friendly, geeky providers that do let you do this stuff. Possibly a little bit less so nowadays, again, because of the pressure on the IPv4 address space. You can do all of this stuff with IPv6, actually, instead. And because that address space is so much larger, this is not a problem. It's easy to get IPv6 addresses. That's a whole other conversation. And we're still at the point where a lot of the internet infrastructure is IPv4. Now, that said, we'll recap a little bit what we talked about last time, which is dynamic DNS, or DYN DNS. And I think this is possibly a bit less used nowadays, but it used to be what most of us did, because back in the day, you know, before fiber to the home and connections to the home, we were doing dial-up networking. So we were using a modem to dial up on a POTS, a plain old telephone system line. And that's where you get this noise, it's connecting up and it's training, and you get onto the internet. Every time you dialed up to do internet-y things, you'd get a different IP address. So if you want other people to be able to access your stuff, it's really difficult, because you're not online all the time, and when you are online, you will have a different IP address from last time. What do? Well, some people took the core of what DNS does, and coming back to your question, you know, I can go to my DNS server and manually type in whatever the IP address setting is I want to. But what they then did was they back-ended it with some automation. So what I could do is, when I dialed up onto the internet and I got given my new IP address, I could make a call, like an HTTP request, to this DYN DNS server to update automatically with whatever the new IP address was. So if that happens automatically every time I connect up to the internet, that DNS server is going to have the new IP address every time I get a new IP address. And then anybody who goes from somewhere else with a URL, as far as they're concerned, it's just the same system. They're doing a DNS lookup. But behind that, it's been automatically updated to a new IP address every time. And also these DNS records have something, I think, which is called a time to live. And you can say, right, I'm pretty sure this DNS record is going to be valid for like a day. So you can cache that for a day before you need to come and ask me again. Or you can say, you know what, this is changing quite frequently, it's going to be valid for 10 minutes, then you're going to have to come and ask me again. So with this kind of setup, you would set the mapping to be valid for a short period of time, and then it would look up more regularly, and then when your IP address changes, it changes, and it knows to use a new IP address. And they exist, and they're out there, and there's free ones, and so for your use case you were talking about last time, if you want to be on the internet and be publicly accessible and not pay for static IP addresses, I wouldn't do this for a commercial, reliable setting, but for testing and things, nothing wrong with using dynamic DNS.
Okay.
Does that help?
Yeah. Thank you.
Anything else? No. Let's wrap it up there then.